With beams and joints defined, now I can move on to defining the operating environment for this weldment. I'll right-click External Loads and select Force. Loads can be applied to reference points, joints, as well as entire beams. Keep in mind that reference points are not vertices nor sketch points. These are points you would create using Insert, Reference Geometry, Point. Also, if applying a load to an entire beam, you can specify the load per unit length using the checkbox below the units list. I'll click the joint icon in the Property Manager to make all joints visible. I'll select the top two joints and apply a 5,000 pound force. I'll use the flat face on the top structural member as a reference for the direction of the force. Notice the force is being applied per entity, so the structure is actually under a 10,000 pound load, 5,000 pounds at each joint. Next, I'll add fixed restraints to 3 lower joints, the free ends of the lower members, and their intersection. This completely defines the operating environment, so we can go on to processing. I'll right-click Mesh and select Mesh and Run. After a short calculation, you'll see stress and displacement results appear in the Results folder. Let's take a look at displacement first. I'll double-click the plot information on the top left to bring up the plot options. Double-clicking, by the way, is a shortcut to right-clicking on the plot and selecting Edit Definition. I'll change the plot to show displacement in the Y direction and click OK. The maximum displacement is about 16 thousandths of an inch. Let's take a look at the stress plot. By default, the plot is displaying the worst-case stress. Worst case combines axial and bending stresses. Again, I'll double-click the plot information to bring up the plot options. Notice I can plot axial and bending stresses individually. Bending stress will differ depending on the direction you're considering. In our case, we're working with rectangular tubing, so bending stress will be different in the longer direction of the rectangle as opposed to the shorter direction. Taking a look at axial stress, you can see that the legend goes from a negative value to a positive value. A negative value, shown in colors below orange, indicates the member is under compression, while a positive value, shown in orange and red, indicates the member is under tension. In addition to stress and displacement plots, you can also view beam forces and stresses in tabular form. To do this, I'll first hide the stress plot and switch to a Shaded with Edges display. This will make it easier to visualize the individual beams. In the Bodies section, notice all beams are numbered 1 through 7. If I wish to examine the forces and stresses for one of the long-angled beams, I first have to know what its number is. Selecting it from the Graphics area, you can see it corresponds to Solid Body 6. Knowing this, I'll right-click the Results folder and select List Beam Forces. I'll select Forces and set the beam range. This will isolate the beam I'm interested in rather than showing a long list of all beams. I'll click OK, and the tabulated data is displayed. Note that data is reported at each end of every element in the beam. Another useful method of reviewing results is to review beam diagrams. I'll right-click the Results folder and select Define Beam Diagrams. You can choose what parameter to include in the diagram: axial force, shear, moment, or torque. Shear and moment can be plotted in direction 1 or direction 2. I'll select moment in direction 1. I'll include all beams in this plot, although you can choose one or more beams using the Select option. I'll click OK, and the moment diagrams are displayed.